Now coming to this type 2 grammars or context free grammars, we have various properties about them. So one is we have various kinds of grammars. In this subclassification is I can classify context free grammars into ambiguous grammars and unambiguous grammars, and other is I can classify context free grammars into deterministic context free grammars and non-deterministic context free grammars, and other is context free grammars into left recursive grammars and right recursive grammars. Okay, so we have all these forms: ambiguous, unambiguous, deterministic, non-deterministic. I mean, I could take the entire class of context free grammars and I could classify them like this, and it doesn't mean that they are all independent. A grammar could be ambiguous and deterministic, I mean non-deterministic or deterministic, and similarly you could think of them as combinations also. So about all these grammars, I have discussed them in detail in compiler design. So I am not going to talk about the types of grammars like this and how to convert one type to other type. Instead of that, we shall discuss some other properties of context free grammars. So in order to complete the study of these context free grammars, I suggest that you even refer to the compiler design lectures. There you will find the entire information. Here I am going to talk about some other properties of context free grammar. Now, one interesting property about context free grammar, or one interesting problem is, given a string w, let us say w is a string now, and given a language context free grammar g, does context free grammar g generate the word w, which means does w belongs to language generated by the grammar capital G? This is an interesting question, which means given a string w, does it belongs to the language generated by the grammar G? So this is an interesting question. How we could answer it is, one thing is, you have to form some algorithm. If you think about the algorithm, so one thing you could come across is, let us say there are p productions in this grammar, then what you could do is take all the strings that could be generated in one step, which means if I have S derives some alpha, where alpha is a string of terminals, then you can think of all such alphas and then compare with w. If anything matches, you can say that yes, w is belonging to that S. Otherwise, if you are not able to do that, then think about set of all strings that could be generated in two steps. Okay, so now then what you do is take all the sentential forms which could be generated in one step, which means let us say I have sentential form like this, and then you take the variable in that and you replace it with a terminal, let us say like this. So if I can get these strings in two steps, then you can find out all the strings which you could get in two steps, and then you compare it with w. If it matches, you can say that w belongs to yes, that language in two steps. Or think about three steps, which means find out set of all strings which could be generated in three steps like this. So let us say S derives small a, capital B, small b, small a, b, something like this, a, b, which means in three steps whatever strings could be generated, you find out all such strings and then compare with w, right? So definitely if w is present in this language generated, then definitely it could be generated in finite number of steps. So if you keep on doing this, like one step derivation, two step derivation, three step derivation, so on, after some case steps, definitely you will be able to say whether w belongs to L of G or not, isn't it? I mean, in case if w belongs to L of G, definitely you will be able to stop this algorithm in case steps. Therefore it is an algorithm, right? And moreover, it is a brute force algorithm. The reason is we are trying to find out all the strings which could be generated in one step, all the strings which could be generated in two steps, which means even though I am showing you only one string, it doesn't mean that I am stopping here. I'll find out all the strings which could be generated in two steps, and there could be many, right? So how many such strings could be there? Many. We shall see that upper bound also later. But one thing you should understand is, if this string could be derived from the language in case steps, this algorithm is going to stop in case steps. What if the given string does not belong to the language? then what happens, you'll keep on generating in a hope that you might generate this string after many number of steps, and we don't know how many, therefore you might get into infinite loop, isn't it? So how could you stop that from happening? So if you have some limit on the length, let us say you found out the length of the string, then you could say that after reaching some few steps, when the length of the sentential form is very much greater than w, you could stop the derivation process. But the problem with such a method is, what if I have some epsilon moves, which means if I have some productions like this, A derives epsilon. If I have such a production A derives epsilon or A derives B, there is no guarantee that this sentential form will not shrink. Because of the productions A derives epsilon, even if you reach a sentential form whose length is 100 now, later you could replace many of the variables in that and you could bring the size of the string to 10. Therefore, if this string is present in the language, you could stop the derivation process in case steps. But if the string is not present in the language, there is no guarantee that you will stop the derivation in case steps. The reason is because of the productions A derives epsilon, you will never be sure when to stop the derivation process. The reason is, even if the sentential form is increasingly growing, but then you could replace the variables in the sentential forms with A derives epsilon, epsilon productions in such a way that you could again get back w. Therefore, there is still a hope that even if you grow the string length to a very large number, you could again get back w. Therefore, your algorithm will never stop. So, if I could do some modifications to the grammar in such a way that there are no epsilon productions and there are no unit productions, which means if I take a context-free grammar, and from this context-free grammar, if I eliminate epsilon productions of this form and unit productions of this form, then all the remaining productions will contain at least two symbols in the right hand side, at least two, isn't it? Then in every step of the derivation, either I will increase the number of variables by 1 or I will increase the number string length by 1, isn't it? Check this, see. Now if I don't have unit productions and if I don't have epsilon productions in the context-free grammar, then what I could guarantee is, with every step in the derivation, we will always increase the string length. We will never shrink the string length. Therefore, after reaching all the sentential forms which are exceeding the string length w, and if w is not yet found, we could discard all such sentential forms. That is the advantage of modifying a grammar so that it will not contain epsilon productions and unit productions, isn't it? If a grammar does not contain epsilon productions and unit productions, then what happens is, in worst case, the entire grammar will be of this form, isn't it? In worst case, A derives BC and A derives A. This is the worst case grammar, right? Which means either all the productions will be simply terminals or there will be two variables on the right hand side. Now, with every step in the derivation process, I either increase the string length by 1, the reason is every variable is replaced by two variables, therefore the string length is going to be increased by 1, or I increase the number of terminals by 1. Therefore, the number of steps which are required to generate a string of length w using such a grammar is, first you increase the length of the string from s, which is 1, to mod w. Therefore, in mod w steps, I can increase the string length to w, and then in mod w steps, I can replace every variable with the terminal. So, in worst case, it takes nearly these many steps in order to generate a string of w, of length w, from a grammar which does not contain epsilon productions and unit productions. Okay, that is the worst case. So our algorithm is supposed to stop after these many steps. Then let's see the algorithm how we could generate it is. In first step, I can have p productions, therefore p sentential forms to examine. I'll examine all these sentential forms and I'll think that if w is present, it's fine. Otherwise, in second step, I'll examine p square sentential forms. How do I get p square is, in every sentential form that I got in the first time, I'm going to replace a variable with all the possible productions. Therefore I might get p square sentential forms in the second round. Then I'll compare all these p square with w. If it matches, fine. If it doesn't match, I'll go to the next step. I'll take all these p square productions and I'll replace every variable with p possible productions. Therefore I might get p cube sentential forms, so on. Finally I might have to examine p power 2w, right? Therefore what is the total time complexity required? Here p square, p cube, so on, p power 2w. It is nothing but p power 2w plus 1, which is exponential. So this algorithm in which we don't have any epsilon productions and unit productions is going to take order of p power 2w steps in order to find out the membership of a string w, right? So we are not going to use such a method. Definitely it is going to be of very large size. So the algorithm is going to be exponential. So we use some other algorithms in order to find out the membership. So basically whatever algorithm you want to use, you should make sure that your context free grammar should not contain epsilon productions 1, and you should not contain unit productions 2, and you should not contain useless symbols. Some symbols will be useless in the grammar. If you eliminate epsilon productions, unit productions and useless symbols, then whatever grammar you get, then you can apply some more conversions to the grammar and you could apply better algorithms. So one such algorithm is CYK algorithm. So using CYK algorithm, we can find out the membership of any string in order of this cube, mod w cube, which means it is a order of n cube algorithm, which is a polynomial algorithm. Okay. So before going to that CYK algorithm, let me talk about how to eliminate epsilon productions, unit productions from the grammars. Okay, we shall see some examples for that now. So just now we have seen that having epsilon productions in the grammar is going to harm the process of derivation. In the sense, we might grow the string length to some extent and again we will shrink it, right? And because of which we are not able to decide till what length we should grow the derivation procedure before stopping and saying that the string could not be generated. Since there is a hope of shrinking, we are going to do it again and again. So just to avoid that, we have to eliminate the epsilon productions, right? So we are going to eliminate epsilon productions, and I'll show you some examples about how to do that. And one thing is, can we eliminate all the epsilon productions from the grammar? If the language generated by the grammar contains epsilon productions, which means if a grammar G is given and if L of G, if you compute the language generated by the grammar, if it contains epsilon, if epsilon is present in the language, then you are supposed to generate epsilon also. Therefore, you will not be able to eliminate all the epsilon productions in case if the epsilon is present in the language. You should at least have one production S derives epsilon. The reason is you should generate epsilon. Therefore, if the language does not contain epsilon, then you could eliminate all the epsilon productions. But if epsilon is present in if that null string is present in the language, you may eliminate all the other null productions except this one, which means you should at least have S derives epsilon. Other than this, you could eliminate all the null productions. Okay, remember this. If the language contains epsilon, you will not be able to generate and eliminate all the epsilon productions. If the language does not contain epsilon, yes, you could do it. Okay, so let me take an example and show you how to do this procedure. We could even know if a language contains epsilon or not also. S derives ASB or AAB, A derives epsilon. If I have any grammar like this. Now first of all, first step is find out all the null productions. So what are null productions here? A derives epsilon, and then find out all the nullable variables. Nullable variable means if a variable can directly generate epsilon, or if a variable can after some number of derivations, if it could generate epsilon directly like this, or after some few number of steps, if it is going to generate epsilon, then also this variable is called nullable. Okay, so find out all the nullable variables in the grammar. So one thing is you found out that A is nullable, isn't it? So nullable variables are, one is A, right? So is S nullable? S is not nullable, because even if if you substitute epsilon here, you are not going to get null. So only variable which is nullable is this A. Then if after finding out nullable variables, go to the right hand side of every production, and wherever that variable is present, write that with it and without it, which means write this production with A as well as without A. Okay, and now you could eliminate this. Okay, after eliminating this, in the production there is no A variable at all, therefore this one also should be eliminated. Therefore the resulting grammar is S derives ASB or AB, right? So what did I do? First step is I found out all the nullable variables. Second step is I have seen all the right hand sides of the productions, and in the right hand side, if there is a nullable variable, I am writing it with it and without it. That is how we eliminated the null productions. Now let's see this one. S derives AB, A derives AA or epsilon, B derives BB or epsilon. Okay, so in this find out what are the nullable variables. So A is nullable, isn't it? Why? It is directly generating epsilon. B is nullable. Why? Because B is directly generating epsilon. Since A and B are nullable, if I put null here and null here, S is also nullable. Now whenever S is nullable, this dot symbol is nullable, it means that definitely S could generate epsilon, therefore epsilon belongs to this language. So in this language epsilon is present. So you may not be able to eliminate all the null productions. You should at least have one null production, S derives epsilon. So let's see how to eliminate this. Go to every right hand side and you try replacing it with and without those nullable symbols. See this? Now A and B are nullable. Let me consider A first. Now write it with A and without A. Therefore I am going to get B. And let me consider B. Write it with B and without B. Then I will get A. Isn't it? With B is AB, without B is A. Then A and B both are nullable, which means I might have to remove both of them. Then I get epsilon. Add it. We are adding a null production. This is a special case only when the left hand side is dot symbol. The reason is, since this dot symbol is nullable, this production should be there, right? So then these need not be there. Now go to every right hand side and write it with it and without it. See this? Now since A is nullable, write it with A as well as without A, which means I get AA, and write it without A as well as with A, which means I get small a, right? So I am replacing one of the A first with epsilon, and then I am replacing both A's with epsilon, therefore I am getting A. And what about this one? See this? Now replace one B, capital B with epsilon, and then replace two capital B's with epsilon. Then what do I get? BB or small b, right? So this is the final grammar in which we have removed all the epsilon productions except the first one, S derives epsilon. The reason is epsilon belongs to the language. Okay. Now see the next one. S derives A, B, A, C, A derives B, C, B derives B or epsilon, C derives D or epsilon, D derives small d. So in this grammar, I have to eliminate all the epsilon productions. So what is the rule? First find out all the nullable symbols. So C is nullable because C derives epsilon is there. B is nullable because B derives epsilon is there. Okay. And since B and C both are nullable, A is also nullable, right? So if you find out, these are all the nullable symbols. So we have A, B, C as nullable symbols. and even if you replace A and C with epsilon, we are not going to get null. So A, B, C are the nullable symbols. Now you could take every right hand side and then you can replace it with and without the nullable symbols. See this? Now since A is nullable, I replace it with A as well as without A. Then what is it? BAC, right? And since C is nullable, I will replace it with it and without it. So what do I get? Since C is nullable, I'll write it with it and without it. And since A and C are nullable, I'm going to write it BA. Okay. Now in this, now B and C both are nullable, therefore I'm going to write it with B and without B, and with C and without C. And since both are nullable, if you replace both B and C with epsilon, you might get A derives epsilon. So we are not supposed to add any epsilon productions, therefore don't replace both of them with epsilon. You have to replace either C or B. If the left hand side would have been this dot symbol, then it means that epsilon is present in the language, then only you are going to replace S with epsilon there, and then only you are going to add S derives epsilon, but in this case don't add it. Okay. Now see this, B derives, yeah, so B derives small b or epsilon. You can replace this, you can remove all the epsilon productions, that's it, right? So you can, in the right hand side, wherever nullable symbol is there, you have written the production with it as well as without it. So that is how we got all these productions. Okay, so this is how we eliminate the epsilon productions. Now if you look at it, eliminating epsilon productions are going to add unit productions, isn't it? So after you are going to get S derives B, or in this case this was already there, but see this, eliminating epsilon productions is going to add unit productions. Now unit productions are also useless. The reason is, if I have any production like A to B and then B to C and then C to small c, let us say C to D is there. In order to generate small d, the procedure is A has to be replaced with B, B has to be replaced with C, and C has to be replaced with D. Now in the entire sequential form, length is not changing, or nothing is changing. The same sequential form is taking different forms, but then finally we are getting the required string. But these entire steps are unnecessary, right? So every step is it has to be useful. Either you should increase the length of the string, or it should increase the number of terminals in the string. But if you look at this, the length of the string is not increasing, or the number of terminals in the string are not increasing. Therefore we are not going to use unit productions in any valid context free grammar. So we want to even eliminate unit productions. So in the next example we shall see how to eliminate unit productions. Okay. So let's eliminate unit productions from this grammar. This is the unit production, right? S derives B, B derives A, and A derives B. So they are all unit productions, and I have already told you that all these unit productions are useless. So how can I eliminate these unit productions? Always remember, whatever transformation we try to do on the grammar, always remember that the language generated by the grammar should not be affected at all. So you could do any number of transformations on the grammar, but finally the language generated should be the same. So even if you delete the unit productions, you should make sure that the final language generated should not be affected. So which means, just see this, say I want to eliminate unit production S derives B, right? If I eliminate S derives B, what are the strings that S might miss out or S might not be able to generate? So if I eliminate this one, what is the effect that S might lose is, see, S might go to B, isn't it? So first of all, first step is you write the grammar without having unit productions. So I am just writing the grammar without having unit productions, which means S derives AA, and then B derives BB, and then A derives A or BC. So I have written all the grammar, all the productions without having unit productions, right? Now just see what are the unit productions in this. The unit productions are S derives B, and then capital B. So if I delete this B, then I might miss out the chance to generate BB. B could have generated BB, therefore S will miss out the chance of generating BB. So you add this. Is this the only chance that S is missing? S could generate B and B could generate A, isn't it? Then A could generate these two. A could generate either A or BC. Therefore, if I delete this entire chain might be broken, and therefore S might miss out a chance of generating A and BC. Therefore, even if you delete, eliminate this unit production, have the effect. What is the effect? A comma BC should still be there. Therefore, I am going to write A and BC. Right. Next one, this one B. So what are the unit productions for B? So one unit production is B derives A, right? Then if I delete this, what is that B is missing out is A could generate A, small a or BC. These two are the chances that B might miss out if I delete A. Therefore, you add those two productions, which means A and BC, right? Now, what is the other one? B could generate A, and A could generate B, which means B is generating B itself. You need not add anything for that, right? And next one is A is generating B. Next production is A is generating B. So if I delete this, what are the chances that A might miss out is A might miss out the chance to generate BB. Therefore, if you delete this chain might get broken. So you should still have the effect. Therefore, you add BB here, right? So that is how. Find out all the chains, and whatever is the result, you add them, and then you can delete it. No problem. Okay. Let me show you one more example for this. Now let's see this. So in this grammar, I want to eliminate the unit productions. How can I eliminate unit productions? Is you find out all the chains and you break them. Okay. So first of all, this is the unit production is B derives C. So first unit production is B derives C. So what is that C could derive? C could derive D. And what is that D could derive? D could derive E, and finally E could derive A. So if I eliminate this unit production B derives C, then B will miss out a chance to derive small a. Therefore, I am going to write small a here. Okay. And anything else that it would miss out? Only this one. Therefore, I could directly eliminate it. Okay. And next one is C to D. If I eliminate C to D, then what is that C will miss out is C will derive D, and D is deriving E, and E is deriving small a. Therefore, C would miss out a chance to derive small a if I delete C derives D. So you could delete C derives D, but then you have small a there. Okay. And now D to E. So if I delete D to E, E could derive small a. Therefore, D has a chance of deriving small a. If I delete it, it would lose it. Therefore, you have it, which means D derives A, right? And one thing, if you observe it, S is deriving AB, and AB are reachable, but these are not reachable. Therefore, these are all useless symbols in the grammar. So now next we shall see how to eliminate such useless symbols. Just see the order. We have eliminated epsilon productions, right? And then we have eliminated unit productions. Now we have to eliminate useless productions. After eliminating that, we are getting some useless productions here, right? So now we shall see how to eliminate the useless productions also. So inside a grammar, there could be many useless symbols. So useless symbols like, so what are useless symbols is, let's talk, instead of talking about useless symbols, let's talk about useful symbols. What are the useful symbols in a grammar? Or if we have a variable a in the grammar, then it is said to be useful if it is able to derive some string, a part of the string. Okay. So if a variable is able to derive a string of terminals, then maybe it might be useful. I am not saying that it will be useful, it might be useful, right? every variable should be able to derive a string of terminals, either one terminal or epsilon or any number of terminals. If a variable, upon doing any number of substitutions, if it is not still able to get rid of some variable, isn't it, then this is not useful. The reason is this variable will never be able to derive any part of the terminal finally derived, right? So one thing is, a symbol is said to be useful if it is able to derive some terminal or some string of terminals. That is first thing. Second thing is, even if it is able to derive some string, if there is no way we could reach from the start symbol to this symbol, then there is no way we could actually use it in any derivation, isn't it? Therefore, first step is every variable should actually derive something, some part of the string, and second step is every variable, that particular variable should be reachable from the start symbol. So first thing is you should see the derivability, and second thing is reachability. If these two things are guaranteed, we can say that the symbol is useful. So how to eliminate useless symbols? I'll take an example, few examples, and I'll explain you. See this. Let us say S derives AB or small a derives BC or small b, B derives AB or C derives AC or B. So these C are all variables. So all these C's are variables, not the terminals. In this, the terminals are a comma b. Okay, how do you identify variables and terminals? Is you need not follow the convention that every variable is capital letter and every terminal is small letter. In the exam, they will even give you what are the terminals. Let us say terminals are given as a comma b, and they will give you what are the variables. Variables are S, A, B, C. These are the variables and these are the terminals. So first step is you have to find out the symbols which are useful. Useful means which will be able to generate some terminal, right? So what are the symbols in this grammar which will be able to generate some terminals? Definitely, you could say that the useful symbols are terminals itself. The reason is these terminals will generate A and B terminals, right? And second step is, after writing the terminals, just see the productions, and in the productions, if the right hand side of a production is only terminal, then you add the left hand side, which means see this is a terminal, right? Purely terminal. Therefore you add S to the set of useful symbols. By S is able to derive something, and then A is able to derive something, B, isn't it? And then B is able to derive nothing, and C is not able to derive anything here. So no terminals. That is second step. And third step is, whatever symbols have been proven to be useful till now, just use those symbols and see if any right hand side of the production is made up of only these symbols. Which means if the right hand side of a production is made up of AB, SA, since we already know that SA and AB are useful, then that left hand side will become useful, isn't it? How? Check this. I'll just take an example and show you. So S is already useful and A is already useful, you need not check about it. Let's talk about B. B, will it be useful? So right hand side contains AB, B is not already proven to be useful, or it is containing C is not already proven to be useful. Therefore this is as of now not useful. Then what about C? Right hand side contains C, it is not useful as of now, and B is also not useful as of now. Therefore these two variables, these two symbols B and C are not useful. The reason is there is no way I could generate any string from this. See, the reason is simple. If you take this B, it will give us AB, isn't it? And again, in place of B, if I put AB, it will give me AAB. If I put one more AB, it will give me AAAB. So there is no way I could ever get rid of B. So in case if you think that I could put C here, then C will never get rid of C, or it will again get B into picture. Therefore B will never be able to generate any particular string. Therefore B is not useful. On the same reasons, C is also not useful. So we found out two symbols which are useless. What next step is, you delete all the productions which are having B and C as left hand side, as well as if they are present in the right hand side, then also you delete them. Okay, so what is remaining now? The remaining is S derives AB or small a derives small b. Oh, this b is also not useful, right? Therefore this also should be removed. This also should be removed. Therefore the remaining productions are S derives A and S derives B. Okay, so now till now what we did is we have seen whether a symbol is deriving some other symbols or not. So according to derivability, it is not able to, we are not able to generate it, so stop it now. Then second thing is see if every symbol is reachable or not. So from S, can you reach A? Obviously there is no reachability, therefore you have to delete this also. How to check reachability is there has to be a path from which S could reach A, but if you start with S, it is going to end in A only, right? Capital A is never reached, therefore this is never possible, right? So the grammar is simply S derives A. Even though the grammar is looking this big, after simplifying the grammar we get only one production, which is nothing but S derives A, and the language generated by the grammar is simply small a. Okay, we shall see more examples. Let's eliminate useless symbols from this. So as always, whenever a question is given, they are even going to give you what are the terminals. So in this, terminals are small a comma small b, and what are the variables? Variables are going to be S, A, B, C, D. So these are all the variables and these two are terminals. Okay, now first find out what are the symbols from which we could derive some terminals or some strings. So useful symbols are going to be the symbols from which we could derive something else, right? So what are the symbols that we could derive some strings here? Definitely the terminals. These are the symbols from which I could derive some terminals or a string of terminals. Okay, and then first of all, we are even eliminating the epsilon productions, so don't worry about it. Epsilon productions are not there and unit productions are not there, then we are going to eliminate this. Now just see what are the variables which are having only A or B on the right hand side. So we see that capital A is having small a on the right hand side, therefore I am going to add capital A, right? And I don't think that any other variable is having simply a terminal. Next step is just see if the right hand side of any other variable is having a combination of A, B and capital A, small b and capital A, if the right hand side of any other symbol. So see this, capital A is having, okay, capital A is already useful, therefore you need not consider about it. Yes, S is not having only these three, right? It is having B or C, so leave it. Look at B. B is having its right hand side as BBA, right? Therefore I am going to add B, right? So why did I add B is, since B is deriving BBA, already B, B and A are known to be useful. How do I know that they are useful? Because of this production, right? So I could use BB and then capital A derives small a, and therefore now B is going to be useful. Already they are known to be useful and they are present at the right hand side, therefore left hand side is also going to be useful, therefore B is useful. Then now check it, this is useful, therefore this is also useful. Now see in all the productions if the right hand side contains only these four. Now check this one, right hand side of S contains only A and B. Already A and B are known to be useful and they are present in the right hand side, therefore S is going to be useful. So S is going to be useful now. And check this, A is useful, B is useful, see if C is useful. If C has to be useful, then its right hand side should contain only these, but its right hand side is containing C and its right hand side is containing D. These are not yet known to be useful. Now let's see this one, D. Its right hand side is containing D, which is not yet known to be useful, and its right hand side is containing C, which is also not yet known to be useful. So these two productions are not going to be useful. I mean these two variables C and D. Only useful symbols are A, B and only these things, right? So if you see any production left hand side or right hand side which are containing any symbols other than this, just to eliminate them. Therefore I am going to eliminate this complete C and this complete D. They are eliminated. And now check this, in the remaining productions, just see that only these symbols are present. If any other symbol is present, you just eliminate it. Now here it is showing that C is present, therefore eliminate this one, and all the remaining are okay, I think. Okay, now these are the productions. So these are all the productions which are known to be useful. I mean, these symbols are known to be deriving some other symbols. In order to find out whether they are useful or not, they have to be reachable from start state. See if A is reachable from S. Yes, A is reachable from S as well as B is reachable from S. Therefore, these are the production. S derives AB, A derives this, B derives this. These are the this is the final grammar which is known to be useful. Let's see one more example. Now let's see this grammar, whether this grammar is useful or not. So first of all, you should identify the terminals. So in this terminals, they will already be given. Terminals are A and B. Okay. Now just find out the useful symbols here. Useful symbols means the symbols, first of all, the derivable symbols, right? Which means the symbols which could derive something useful, like terminals. So the starting set is A comma B, because A comma B, they will generate all the terminals AB and their combinations. Therefore, these two symbols are found out to be deriving some strings. And then check the productions. If the right hand side of the production is going to contain only these two symbols, then you add them. So I see that B is the only variable, and then okay, A is also a variable. A and B are going to contain only terminals in the right hand side, therefore I am going to use them, write them as they are going to derive some variables. Okay, now see the right hand side of the productions, they have to contain only A, B, capital A and capital B. So this is the production which contains B and small. These three are useful, these three are already deriving something. Therefore, S is going to derive something, and we have already added A, and then we have already added B, and this one cannot be added because in order to add C, I need C, but C is not yet proven to be useful. Therefore, these are the symbols which could derive something. So, if there are any productions which contain other than these symbols, you just eliminate them. So these all have to be eliminated, and check this A, B, C. This A, B, C, this production has to be eliminated, and then there is C, this production has to be eliminated. What about this? Only B and A. Yes, it should be left there. A and B, it should be left there, and A left there, B left there. Okay, leave it there. So this is the final grammar which contains which does not contain any useless symbols. S derives BAB, A derives AA or AAA, B derives this. Okay. Now you have to check whether they are actually reachable or not, right? So these symbols are all deriving something, but then they should even be reachable from S. So see, from S we could reach B, but from S we cannot reach A. See, from S I could reach B, isn't it? What is the production? S derives BAB, but from B I am not able to reach capital A. Therefore, you have to eliminate capital A production also. So finally, the remaining productions which are useful is S derives BAB, B derives BBB or small a. These are the useful productions. Okay. So that is how we eliminated the useless productions, right? So we shall continue to the next topic. Next topic is push down automata.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So, first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into universities better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.